In the last few days, a volcanic island sitting in the Sunda Strait of Indonesia sent a plume of gray ash into the sky, and the moment it happened, monitoring stations that had gone quiet for months snapped back into full alert. On its own, that plume looks almost forgettable, barely 100 meters high, the kind of thing you'd scroll straight past on a news feed. But this island has a name, and once you know that name, this stops being a small story. This is Anak Krakatoa, the child of Krakatoa, the volcano that grew back out of the wreckage of one of the deadliest eruptions in recorded human history. And the last time this mountain stirred like this, it killed hundreds of people who never even felt the ground shake. Stay with me for the next few minutes because by the end of this video, you will understand something most people watching the news right now do not. Why a plume this size is being treated as a serious event by the people whose entire job is to watch this mountain and exactly what they are bracing for next. Let's start with what actually happened because the details matter more than the drama. Over the past several weeks, a volcanic island sitting in the Sunda Strait, the narrow channel of water separating Java and Sumatra in Indonesia, has been sending up plumes of ash that rise only around 100 meters above the crater. To put that in perspective, that is roughly the height of a 30-story building. In the world of volcanic eruptions, where some ash columns punch 20 or 30 kilometers into the stratosphere, a 100-meter plume is nothing. If you were scrolling through a list of global eruptions ranked by size, this wouldn't even make the page. And if this were almost any other volcano on Earth, that would be the end of the story. A little smoke, a little ash, back to business as usual. But as you already know, this isn't almost any other volcano, and the same young restless island has already proven once in living memory that it does not need a large eruption to kill hundreds of people without warning. We'll get to exactly how, but first, here's the detail that tells scientists this isn't just routine venting. Here's the detail that separates people who understand the story from people who are just watching a headline scroll by. It is not the height of the plume that matters, it is the color. When a volcano releases a plume that is white and billowy, that is mostly steam water vapor, escaping from a system that is doing what volcanoes do on a quiet day, it is the mountain breathing. But when the plume turns gray, the story changes completely. Gray means the volcano isn't just releasing gas anymore. It means solid, fragmented rock is being carried up and out of the crater along with that gas, and rock doesn't ash itself for no reason. For fresh material to be entering that plume, magma has to be close enough to the surface to be breaking that rock apart. A white plume tells you the volcano is alive. A gray plume tells you the volcano is active right now, at a depth shallow enough to matter. That is why the people monitoring this island didn't shrug this off as background noise. That is why the moment the plume shifted, color alarms started going off inside monitoring stations that had been quiet for years. But the plume alone isn't the full picture, and if you only pay attention to headlines, you're going to miss the part that actually worried scientists in the first place. This didn't come out of nowhere. It came at the end of nearly 3 weeks of steadily building activity. And when you lay that timeline out day by day, the pattern becomes impossible to ignore. In early June, satellites orbiting overhead picked up something scientists take very seriously. A spike in sulfur dioxide gas rising from the volcano paired with a thermal anomaly, a patch of heat on the surface where there shouldn't have been one. That's often one of the earliest fingerprints of magma creeping upward inside a volcanic system. Around the 10th of June, a distinct hotspot appeared directly inside the crater, visible to infrared satellite instruments passing overhead. Then on the 18th and 19th of June, the ground itself started talking. Instruments recorded a sharp rise in shallow earthquakes beneath the island, small tremors that most people would never feel, but that seismographs picked up clearly. And since the 26th of June, both the frequency of those earthquakes and the intensity of the ash-laden smoke pouring out of the crater have climbed again. Gas, heat, shaking ash. Each one on its own could be explained away. Put together in that order over that time frame, they tell one consistent story. Something is moving underneath that island, and it's moving toward the surface. Now, here's where most coverage of stories like this stops and where I want to actually slow down, because this is the part that separates a genuine scientific concern from internet panic. Not all earthquakes under a volcano mean the same thing. Scientists who monitor systems like this one don't just count tremors and move on. They classify them because different types of shaking come from completely different physical processes happening underground, and reading them correctly is the difference between an accurate warning and a false alarm. Some of the earthquakes recorded under this volcano are what's called hybrid earthquakes. These happen when solid rock is physically fracturing at the exact same moment that magma gas or superheated fluid is forcing its way through cracks in the shallow part of the volcanic system, essentially punching through rock under pressure. Other signals are called low-frequency earthquakes, and these have a completely different signature. Instead of the sharp snap you get from rock breaking, these come from fluid and gas moving through the plumbing of the volcano, more like the rumble you'd hear from something forcing its way through a pipe than the crack of stone splitting apart. And then there's continuous tremor, which isn't a series of individual pops at all, but a sustained ongoing vibration, the kind of signal that tells scientists the entire system is active over long stretches of time rather than just twitching occasionally. There's one word buried in all of this that deserves your full attention, and it's the word shallow. Volcanic earthquakes can happen at all kinds of depths, and depth changes everything about what the activity actually means. If earthquakes are happening deep under a volcano, that can mean magma is still far down in the system with a long, slow journey ahead of it before it does anything visible at the surface. That's activity worth watching, but it's activity with time attached to it. When the earthquakes start clustering at shallow depth, though, the math changes completely. Shallow means the action is moved close to the top, close to the crater, close to open air. When you combine shallow earthquakes with a fresh thermal hotspot and a plume that is visibly shifted from white to gray, you're no longer looking at a volcano quietly, thinking about waking up somewhere deep in its plumbing. You are looking at a volcano that already has fresh material sitting right near the surface, actively venting into the sky above it. That is a real, measurable step up from the slow, sleepy background hum this island produces, even in an ordinary quiet month. To be completely fair to the science, and to avoid falling into the trap of treating every single one of these signals as proof of imminent disaster, it's worth saying. Clearly, none of these indicators on its own guarantees a major eruption is coming. A gray plume can fade back to white within days. Shallow earthquake swarms can settle down without ever producing a significant eruption. Volcanoes tease. They rev up and stall out constantly, and most of the time nothing dramatic follows. But what makes this specific situation different is convergence. It's not one instrument showing one anomaly. It's multiple independent systems, gas sensors, thermal cameras, seismographs, all telling the same story at the same time, all pointing in the same direction. That convergence is what separates a genuine reactivation from the random background noise a restless volcano produces on any given week. When gas, heat, shallow, shaking, and ash all rise together over the same 3-week window, that's not coincidence, that's a pattern. So, what have Indonesian authorities actually done about it? Indonesia's Volcanological Monitoring Agency has placed this volcano at the second level on a 4-tier alert scale. In Indonesian, that level is called waspada, which translates roughly to be on guard or be alert. It's an advisory level classification, not an emergency declaration. Alongside that, alert level officials have drawn an exclusion zone roughly 2 kilometers wide, a little over a mile around the active crater, and the public has been told firmly to stay out of it. It's worth being precise here because precision is exactly what gets lost in translation whenever a story like this spreads online. Level 2 does not mean a catastrophic eruption is confirmed to be coming. It does not mean disaster is imminent. What it actually communicates is narrower and more honest than that. The system is active. Something measurable is happening at shallow depth, and it deserves close, continuous monitoring. That's not a prediction. That's vigilance. And understanding that distinction is going to matter a lot by the time we get to the end of this video. Now, let's zoom out, because to really understand why this particular island commands this level of attention, you need to understand exactly where it sits and what kind of geological neighborhood it lives in. Anak Krakatoa is a young volcanic island rising out of the Sunda Strait, the body of water that separates the Indonesian islands of Java and Sumatra. It exists because of one of the most violent tectonic collision zones on the entire planet. Beneath this stretch of ocean, the Indo-Australian tectonic plate is being forced downward driven beneath the edge of the Eurasian plate along a feature called the Sunda Trench. That collision, called a subduction zone, melts rock deep underground and feeds a long chain of volcanoes running the entire length of Indonesia. This chain is part of what's widely known as the Pacific Ring of Fire, the horseshoe-shaped band circling the Pacific Ocean where the vast majority of the world's earthquakes and volcanic eruptions occur. And within that entire ring, Anak Krakatoa stands out as one of the most closely watched and unpredictable members of the family. Because this volcano is an island sitting in open water inside a narrow strait, its dangers aren't limited to the ones you'd picture from a mountain rising out of solid land. Yes, it can throw ash lava fragments and volcanic bombs skyward. Yes, it can send pyroclastic flows, superheated avalanches of gas and rock racing down its slopes at devastating speed. But part of its threat doesn't move upward or downward, it moves sideways, and it moves underwater, where cameras and casual observers can't see it happening. Material from the volcano's flank can slide directly into the sea. The structure of the cone itself can fail, and that opens up a category of danger that a purely land-based volcano simply doesn't have the ability to displace an enormous volume of seawater all at once. Here's why that risk is especially sharp right now. This island is young, and geologically speaking, it is loosely built. Since a major collapse event in 2018, which we're going to get to in detail, the volcano has spent years actively rebuilding itself. Stacking up a fresh cone made of poorly consolidated volcanic rock directly on top of the scar left behind by that earlier failure. That detail isn't a side note. It's central to the entire risk profile of this mountain. A cone built from loose, fragmented material piled up on a steep slope that runs from above the waterline straight down into open ocean is inherently far more prone to collapse than a mountain carved from solid bedrock. Picture the difference between a hillside made of solid granite and a mound of loose gravel poured onto a ramp. The granite holds its shape under pressure. The gravel just waits for a reason to slide. Under the weight of continued eruptions, the pressure of rising magma pushing up from below, or the shaking from an earthquake swarm, a structure built like that can give way. This volcano is quite literally rebuilding the same unstable shape in the exact same volatile location where its predecessor already failed catastrophically once before. And that is the threat connecting a small gray plume today to a very real danger tomorrow. There's one more feature of this location that makes everything more dangerous, and it's easy to overlook if you're only thinking about the mountain above the waterline. The slope of this island doesn't stop at the shore. It continues underwater, dropping away beneath the surface into deeper water. That means when a section of the cone eventually fails, it doesn't just tumble onto a beach and stop. It plunges straight into the sea and keeps sliding, dragging more loose material down with it as it descends beneath the surface. The total volume of rock involved in a flank collapse can be far larger than anything visible from a boat or drone above the water. It's that submerged, sliding mass, the part nobody can see, that does the actual work of violently shoving the ocean out of the way. This is exactly why a volcano that can look almost sleepy from a passing ship can still be one of the most dangerous geological structures in the entire region. Most of the loaded gun sits below the waterline, invisible to anyone just glancing at the island from a distance. Now we get to the core of why scientists are watching this mountain so closely, and it has almost nothing to do with how tall the ash column climbs on any given day. The real defining threat from this volcano is a chain reaction, and once you understand the sequence, you understand exactly why a 100-meter plume can matter more than it looks like it should. It begins with an eruption. That eruption destabilizes the loosely built cone sitting on top of the island. A section of that cone's flank collapses into the sea. The sudden collapse shoves an enormous volume of water out of the way almost instantly. And the result is a tsunami not generated by an earthquake rupturing along a fault line, but by a landslide of volcanic rock crashing into the ocean. It is a tsunami with no fault rupture behind it, and that single distinction changes everything about how dangerous it actually is. Think for a second about how most people are taught to understand a tsunami warning. When a massive earthquake strikes along a subduction zone, the ground shakes often violently, often for a minute or more. That shaking functions as nature's own alarm system. It's the exact cue that has been drilled into coastal communities around the world. From the Indian Ocean tsunami of 2004 to the disaster that struck Japan in 2011. The message is simple, and it's been repeated for decades. If the ground shakes hard near the coast, move to high ground immediately. That shaking buys time. Sometimes only a few minutes, but minutes that have saved thousands of lives. A volcanic flank collapse tsunami removes that alarm completely. Water can be violently displaced by a sudden structural failure with little to no significant earthquake attached to it at all. There's no long period of shaking, no obvious physical cue, nothing for the human body to instinctively recognize as danger. The wave simply arrives. And that is the unresolved warning problem sitting at the center of this entire story. Is it even possible to get ahead of a threat like this? Can the kind of monitoring we just walked through, the shallow earthquakes, the gas readings, the thermal signatures, the subtle deformation of the ground, actually give scientists enough lead time to anticipate a flank collapse before it physically happens? Or is a silent earthquake free? Tsunami simply a hazard that by its very nature can strike, faster than any warning system built today can respond. These aren't abstract theoretical questions being debated in a classroom somewhere. This volcano has already run this exact experiment once, on a real coastline with real families standing on real beaches. And the outcome of that experiment is the entire reason anyone is paying close attention to a gray ash plume right now. In December of 2018, this precise chain of events played out in full. A major eruptive episode at the same volcano caused a large section of its flank to collapse directly into the sea. The cone built from that same loose, poorly packed volcanic rock simply gave way. The collapse displaced a massive volume of seawater and sent a tsunami racing outward across the Sunda Strait. And it did exactly what the underlying science says this specific kind of event does. It arrived with no large earthquake behind it. There was no extended period of ground shaking to warn anyone standing near the shore. People on the coast had no physical reason in the moment to run. And to make matters immeasurably worse, it happened at night, meaning people couldn't even see the wave approaching across the dark water until it was already on top of them. It was also the holiday season, and the beaches and coastal resorts on both the Java and Sumatra sides of the strait were packed with vacationers, precisely because it was a time of year when people wanted to be close to the water. The waves struck communities that were near the coast for the exact reason that made them vulnerable. At least 437 people were killed that night. More than 1,4,0,0,0 people were injured. Tens of thousands were displaced from their homes almost instantly. On the small islands closest to the volcano itself, inside what's known as the crater complex, water surged up the land to heights exceeding 80 meters, more than 260 feet, an almost unbelievable number that reflects just how close those tiny islands sit to the point of collapse and how local geography can concentrate and amplify a wave's power. On the more populated coastlines of Java and Sumatra, further from the volcano itself, the waves still reached heights of up to roughly 13 m, around 43 feet. It's worth pausing on what those numbers actually mean because the human imagination tends to picture tsunamis exclusively as towering cinematic walls of water, and it tends to mentally dismiss anything smaller as harmless. The reality is far more unforgiving. Even a small wave is lethal. A wall of moving water just 1 meter high, and in some situations even less than that, can kill a person outright. A wave only 3 feet tall carries enough force to knock a full-grown adult completely off their feet and drown them where they stand. The reason is simple physics. A tsunami isn't a single cresting wave like the ones surfers ride for fun. It's the ocean itself rising up and surging onto land and carrying the full accumulated weight of moving water behind it. And that water keeps coming, dragging debris, snorts, vehicles, and entire structures along with it as it advances. The coastal waves that struck in 2018 were several times taller than that lethal threshold, and they arrived in complete darkness with no announcement at all. The aftermath of that night also exposed something deeply uncomfortable about how unprepared the entire region was for a tsunami that broke every rule people had been taught to expect. Warning systems across that part of the world had been built, tested, and rebuilt around earthquakes, around the fundamental assumption that the ground would shake first and buy everyone a precious handful of minutes to react. When the wave arrived with no earthquake behind it at all, that entire assumption simply failed. Some coastal communities reported feeling absolutely nothing before the water reached them. Others described pure confusion. People standing on the beach in the dark watching the sea behave strangely with no mental framework at all to understand what they were actually looking at until it was far too late. That gap, the space between the real threat and the warning systems built to catch it, is the single most important lesson the 2018 disaster left behind. And it is the exact reason the unrest happening right now, weeks of gas heat, shallow earthquakes, and a shifting plume, is being taken as seriously as it is. This isn't paranoia. This is a region that has already paid the price once for underestimating this mountain, and nobody wants to pay it again. There's another layer to why this specific volcano commands the kind of attention most volcanoes never get, and it has to do with the name it carries and the catastrophe it was quite literally born from. The parent volcano Krakatoa exploded in August of 1883, and it remains to this day one of the most violent volcanic events ever recorded in human history. That eruption destroyed roughly 2/3 of the original island outright. The northern portion of the mountain collapsed beneath the sea, leaving behind a massive drowned crater, a caldera, the very basin in which the current volcano has been slowly growing ever since. The ash column from that eruption climbed to somewhere around 80 kilometers, nearly 50 miles into the sky. The explosion itself was heard thousands of kilometers away, recognized today as one of the loudest sounds ever documented in recorded history, and the atmospheric pressure waves it generated actually circled the entire planet multiple times, registering clearly on barometers as far away as London and Washington, D.C. The death toll from that eruption in 1883 stands at approximately 3,6,000 people. And here's the detail that ties this entire story together into one continuous thread. The overwhelming majority of those deaths did not come from lava, ash, fall, or the force of the explosion itself. They came from tsunamis. The largest waves recorded in nearby bays reached roughly 41 m, about 135 feet. The lesson written in 1883 and repeated again in 2018 is exactly the same lesson. In this particular stretch of ocean, the real killer has never been the fire. It has always been the water. That is why a volcano quietly rebuilding itself inside the collapsed crater of a catastrophe on that scale is watched with a level of seriousness that a small gray plume on almost any other mountain on Earth simply would not earn. It's important in the interest of staying accurate and not sliding into exaggeration to be honest about scale here, because this is exactly where a lot of online discussion goes wrong. The 1,883 eruption is classified as a 6 on the Volcanic Explosivity Index, a scale scientists use to measure the size of eruptions, and a 6 is officially described using the word colossal. You'll often see people online attach the term supervolcano to Krakatoa, and that label is simply incorrect. A genuine supereruption, an 8, on that same scale involves the ejection of more than 1,000 cubic kilometers of material, roughly 240 cubic miles. The 1,883 eruption, devastating as it undeniably was far smaller than that threshold, And buried inside that correction is arguably the single most important point in this entire video. The real danger from this volcanic system has never actually required a super eruption to cause mass casualties. The tsunami that killed hundreds of people in 2018 was produced by a comparatively small flank collapse, not by some colossal world-shaking blast. The threat here doesn't need to be enormous to be lethal. It only needs to move the water. Now, whenever a volcano with a history like this one starts stirring, a predictable wave of theories spreads across social media, and those theories deserve a direct, honest answer rather than a polite silence or an eye roll. One claim that circulates is that unrest like this is being deliberately triggered by some kind of secret technology, a directed energy weapon, or an atmospheric heating device. There is no known physical mechanism by which any human-built technology could inject magma into a volcanic system or drive the immense geological engine of a subduction zone. The raw energy involved in moving molten rock through the crust of the Earth dwarfs anything human machinery can produce by a margin that's almost impossible to put into everyday terms. What's happening beneath this island is a textbook expression of the Sunda subduction zone monitored in real time by instruments that measure earthquakes, gas emissions, and ground movement. The exact same kind of instruments used to monitor volcanoes all over the world. A second claim suggests that authorities are secretly hiding an imminent mega eruption from the public. The reality is essentially the opposite of concealment. The published alert level and the clearly marked exclusion zone are themselves the open public communication of risk, not evidence of a cover-up. And a third theory tries to link solar storms or space weather to volcanic eruptions for which there is no established scientific connection to magma movement whatsoever. The genuine documented danger sitting inside this story is frightening enough on its own. It doesn't require any hidden or exotic explanation to justify taking it seriously. So where does an honest assessment actually land? It sits deliberately between two very different mistakes, and understanding both of them is the whole point of this video. The first mistake is to minimize what's happening, to wave it off as just steam or just a tiny plume, nothing to see here. This volcano's own documented history makes that kind of complacency genuinely inappropriate. The second mistake is to catastrophize, to treat a 100 meters ash plume and a level 2 advisory alert as proof that an 1883 scale eruption or an immediate flank collapse is bearing down on the strait tomorrow. Nothing in the current data supports that conclusion either. The correct posture, the one that the scientists actually monitoring this mountain around the clock have taken, is vigilance without panic. This is a real measurable escalation above background activity, occurring on the one volcano in the region that has already proven twice over exactly what this specific chain of events is capable of doing to the people living along its shores. That is precisely why it's being watched this closely, and why the watching itself is the real story here, not speculation about what might happen next. So, what actually happens next? The honest answer is that nobody knows for certain, and the scientists closest to the raw data are the first people to say so openly. What they can tell you with real precision is exactly what they're watching for the specific signals that would shift the situation from a standing advisory towards something considerably more serious. They're watching to see whether the ash columns grow taller, stronger, or more sustained over time. They're watching whether the continuous tremor beneath the island intensifies, and whether the low-frequency and hybrid earthquakes we talked about earlier become more frequent and more energetic. They're watching for visible incandescent lava appearing at the crater rim, for measurable swelling or deformation of the ground that would suggest magma physically pushing the structure toward instability from below, and for any official decision to raise the alert level beyond where it currently sits. A meaningful change in any one of those signals would move the needle significantly and would likely be the first thing you'd hear about if it happened. What makes this moment genuinely worth paying attention to isn't just the volcano itself, it's that this is, in a very real sense, a live test. The disaster of 2018 exposed a brutal, painful gap in how coastlines around the world protect themselves. A category of tsunami that strikes without the earthquake warning everyone has been trained their entire lives to recognize. In the years since that night, the underlying question monitoring agencies have been quietly wrestling with is whether the lessons of that disaster could actually be turned into a system capable of catching the next collapse before it happens rather than after. The reactivation unfolding right now, the gray plume, the shallow earthquakes, the rising tremor, is effectively that system being tested under live real-world conditions. Whether it can ever provide enough warning for a hazard that moves this fast remains the open, unresolved question hanging over the entire strait. For right now, today, the practical reality is straightforward, and it is not on its own a reason for alarm. The exclusion zone around the crater exists for a very specific reason, and it should be respected without exception by anyone near that coastline. The alert currently sits at level 2, not higher. The plume remains small, the activity remains centered at shallow depth, and the entire situation is being monitored closely around the clock by people whose full-time job is to catch the exact moment any of this changes. What you now understand that most people scrolling past this story never will is why a plume this modest is being treated with this much seriousness. It was never really about the height of the ash column. It's about the volcano sitting underneath it, the coastlines curling around it, and the history written into both of them. A history that has already claimed tens of thousands of lives across two separate disasters more than a century apart, from a mountain that keeps rebuilding itself in the exact same unstable spot. We are going to keep watching this one closely because the next update could come in hours or it could come in months. And when it comes, you're going to want to already understand every piece of context we just walked through instead of trying to catch up in real time while a headline is already spreading. If this kind of grounded, evidence-based breakdown is something you want more of, subscribe now so you don't miss the moment this situation changes. Hit the notification bell so the next update actually reaches you the second it's posted, and drop a comment telling me which region you think deserves this same kind of deep, honest look next. We read every single one. We'll be back the moment there's something real to report.